We now begin the next section where we will discuss derivatives. And the good point to start is to review some of the basic things that you learned in regular calculus. For that, let's look at a simple picture. So let's suppose we have a graph of some function f of x. That is going to look like this. F of x, x, like this. So I'm going to have few special points here. Then maybe we have a jump, and then a vertical asymptote, let's say. So our 4 points are going to be A, B, C, and D. And let's see, so what was the definition of the derivative that was given in regular calculus? It was basically defined as a slope of a tangent line to the graph of your function at a particular point. So in order to figure out and actually, sorry, I forgot to finish drawing the graph of the function. So in order to figure out no, that's not what I wanted. I wanted something like this. So derivative is a slope of a tangent line, and what we want to do is to draw tangent lines to the graph at different points. So at point A, it seems that the tangent line is going to be just a horizontal line. At point B, things are not so clear-cut because at B I have a corner, and so anything that touches a graph, any line that touches a graph at this corner will be a tangent line. In case C, well, is there a tangent line here? No, right? Because the graph is jumping. In fact, I have two different branches to it, so I can legitimately say that something like this is a tangent line, something like that is a tangent line, so a tangent line is not unique in this case. And at D, my function is not defined, so there's no tangent line there. But the slope of a tangent line as x approaches D, the slope of a tangent line becomes larger and larger, so it becomes infinite. So derivative at x equal to A is equal to the slope of tangent line at A. At A. And if you remember, we know that if f is differentiable if f has a derivative at A, we say that, or at x equal to A actually, then f is differentiable at a. Number 3, so again, per picture that I just drawn, right, we have some special points here. Corner, there is no derivative because there are infinitely many possible tangent lines, so there is no unique derivative. Jump, again, no unique derivatives. So a couple of conclusions that we can draw from this. So if the function has a discontinuity at a certain point, right? So for example, here it has discontinuity at C. At D, even if the function continued beyond D, maybe if it was like this, at D, derivative is not defined because there is no slope in this case as well. So if the function is discontinuous at a point, then it doesn't have a derivative. It cannot be differentiable there. So f discontinuous at x equal to a, again, that's x equal to a, not necessarily on a picture, implies f is not differentiable at a. And maybe one more item. What if the function is differentiable at a certain point? If it does have a tangent line, like it does have it here, then does it seem that the graph is continuous? Yes, right? So it's not difficult to conjecture that whenever the function is differentiable, whenever it has a tangent line, it must be continuous, right? If it has a tangent line, locally it looks like a straight line, and a straight line is a continuous function. But on the other hand, is it true that if a function is continuous, it must be differentiable? Well, it certainly seems so in the highlighted area in the picture. But then if I look at the corner, right, then my function is not differentiable there. So that means that from this example, we can conjecture that if the function is differentiable, then it must be continuous, but if it is continuous, it does not have to be differentiable. So that's another fact that I would want to list here. F is differentiable at x equal to a should imply that f is continuous at x equal to a, but not vice versa. Right, and vice versa, not vice versa. Why? Because if f has, not f, but if the graph of f, let's say, if the graph of f has a cusp or a corner, at x equal to a. Right, so that was our example here. Okay, so then what did we do to define the derivative analytically? So geometrically, it's fairly clear what it is, right? All of these conclusions that I have just drawn, I'm simply drawing them from the picture. What was the definition of a derivative, and what was it motivated by? Again, another picture. So y-axis and x-axis again. So f of x and x. And let's say I have a graph of a function like this. I pick a specific point. Again, that point is going to be x equal to a. Clearly, this function has a tangent line. So like this. And I want to figure out what the slope of a tangent line is analytically. So I want the slope of a tangent line. Well, but actually, in order to find the slope of a line, what do I need to do? I need to divide rise by run, delta y by delta x. And if I'm computing the slope at a single point, then clearly there is only one point. So I cannot use one point to find the slope. So the trick that we used back in calculus was this. You would consider a different point x away from a. And then through f of a and f of x, you draw another line, like so. So green is a secant line, and red, again, is a tangent line. And so then the slope of a secant line was, as a slope of any line is, actually let me use different color here. Slope of a secant line was f of x minus f of a divided by x minus a, right? The rise over run for the secant line. And we say that the slope of a tangent line you're going to obtain by making a secant line as close as possible to a tangent line. How do you make them close to one another? You take the point x and you move it closer and closer to a. So what you do is you take a limit of the slope of a secant line as x goes to a, and what you get then is the slope of a tangent line. All right. Okay, and with that, we now have a sufficient background to just go ahead and analytically define the derivative of f of x, and then once we have a definition, we should be able to deduce all the properties that I have listed here, along with many other properties, like a derivative of a sum, derivative of product rule, chain rule, and so on. Okay, so let's get on with it. Then, definition of a derivative. We identify the derivative with the slope of a tangent line. So, given a function f of x, f of x with some domain that includes, actually let me rephrase this, given a function f defined on an open interval that contains point A the derivative of f at a is given by f prime of a, or also df dx at a, or also we use a different notation, fx of a. There's some other notations that I'm not going to list here. So all of these things, this is a derivative of f at a, and it is defined as a slope of a tangent line. So we use this expression for the definition. So it is a limit x approaches a of f of x minus f of a divided by x minus a. Let's also provide an alternative expression for this, which you already know. If I make x minus a equal to delta x, then x will be a plus delta x, right? And if x goes to a, then delta x goes to 0, right? So then we can write the definition the following way: f prime of a is equal to the limit. So again, x goes to a, delta x goes to 0. And delta x approaches 0, and here I have f of x now becomes f of a plus delta x minus f of a divided by delta x. Right, so this would be an alternative definition. And let's now do a couple of examples. So example number 1. Let's consider f of x equal to x squared, and let's make a equal to 1. Then how do I compute f prime of 1, right? So at this point we don't have any simple formulas. I mean, we do, but we pretend that we don't know them. We don't know that the derivative of x squared is 2x, so we have to compute this directly by using the limit definition. So what is that? That's a limit as x goes to 1, right, of f of x minus f of 1 over x minus 1, which is a limit x goes to 1. What's f of x? F of x is x squared. And what is f of 1? It's 1 squared divided by x minus 1. Now, x squared minus 1, well, first of all, if x goes to 1, top and the bottom both go to 0, so you get an indeterminate form. So what you would need to do is first you would need to simplify and then use the properties of a limit. So, same as a limit when x goes to 1 of x minus 1 times x plus 1 over x minus 1. X minus 1 cancels out. This is a limit x goes to 1 of x plus 1, which is 2, right? So the conclusion is that f is differentiable at x equal to 1, and f prime of 1 is equal to 2. Example number 2. Same question, f of x is absolute value of x, and I want f prime of 1, and I also want f prime of 0. Let's compute f prime of 1 first. F prime of 1 is a limit x approaches 1 of what? F of x minus f of a, so absolute value of x minus absolute value of 1 divided by, divided by x minus 1, right? So I need to simplify this because I don't know how to manipulate things with absolute values. Well, in this case, clearly absolute value of 1 is going to be 1, right? It's a positive number. And what about absolute value of x? Well, when I take a limit, when x goes to 1, x approaches 1, x near 1 must be positive, right? So x is, roughly speaking, equal to 1 in this case. So absolute value of x is the same as x. And so then we're taking a limit, x goes to 1 of x minus 1 over x minus 1. Notice this is still an indeterminate form, but of course, x minus 1 over x minus 1 is just a fancy way of writing 1. And limit of 1 is 1. So conclusion here, f is differentiable at x equal to 1, and f prime of 1 is 1, right? That's easy. Part B. Let's do the same thing at 0. What is f prime of 0, right? That should be basically a very similar expression. Limit x now goes to 0 of absolute value of x minus absolute value of 0 over x minus 0, right? This should be an indeterminate form once again. And it is, right? Because top goes to 0 and the bottom goes to 0. I can make this easier by getting rid of 0. So what I need to compute is a limit of absolute value of x over x when x goes to 0. Okay, when x goes to 0, x is near 0. Before x was near 1, so then I could have removed the absolute value sign. But in this case, x is close to 0, so that does not preclude it from being either positive or negative. And so then what I can do in order to compute this limit, I can look at the limit from the right and from the left, and if those are the same, that would be my limit. So I'm going to check, first of all, limit x goes to 0 minus of absolute value of x over x. And the limit as x goes to 0 plus of the same thing, absolute value of x over x. What's the first guy? The limit x goes to 0 minus. If x goes to 0 from the left, it stays negative, right? And if it stays negative, then absolute value of a negative number is a positive number. So absolute value of x is minus x. On the bottom, it's still x. So then x cancels out, and the limit of minus 1 is just minus 1. In a similar way, if I take a limit from the right, x goes to 0 from the right, so it remains positive. Absolute value of the positive number is itself x over x, that's a limit of 1, and so it is 1. These two are not the same number. So, not the same. And therefore my original limit does not exist, right? Because limit from the right and limit from the left should be the same for the derivative to exist. And so the conclusion here is that f is not differentiable. At x equal to 0. Right, and that's clear why it is so, because if I draw a simple graph of absolute value of x, then it has a corner at x equals 0. Well, I know that somehow from the beginning, that there is a corner at x equal to 0. But also the computation that we just did, in fact, establishes that you have a corner at x equal to 0 because you're approaching 0 at different slopes from the right and from the left. So the slope from the right is 1, slope from the left is -1. So that means that you must have a corner.